So hello, everyone. Thank you for joining us today. We are very excited and happy to have you join our fifth MoroccoAI webinar of this 2022 AI webinar series. A brief intro about MoroccoAI and who we are. We are an initiative led by AI experts in Morocco and abroad. These experts are professors, researchers, and AI professionals. Our main mission is to promote AI growth in Morocco and build a strong collaborative AI community, both locally and abroad. We have launched different activities such as AI webinar series. The AI webinar series aims to bring AI researchers to present and share their work with the community. You can rewatch them in MoroccoAI website or our YouTube channel. For today's webinar, Ridwan and I will be your host. I will let Ridwan introduce himself.
Hello, everyone. My name is Ridwan Gansat, and I'm a research engineer at the IPSL Climate Modeling Center. Happy to be here and looking forward to Maha's talk. And welcome, everyone.
Thank you, Ridwan. So I am Iman Khouja. I have PhD in NLP, and I am currently a data scientist. And don't forget to follow us on LinkedIn, Twitter, and Facebook, and join our community on Slack to be notified about our upcoming webinars and other activities. In this fifth webinar of 2022, Dr. Maha Elbayad will be presenting No Language Left Behind project, Meta latest breakthrough in machine translation on scaling human-centered machine translation, where Dr. Maha will detail datasets and models aimed at narrowing the performance gap between low and high resource languages in machine translation. Dr. Maha is an AI research scientist at FAIR, Meta AI, working on massively multilingual machine translation models. She completed her PhD in 2020 from Université Grenoble-Alpes, where she worked at LIG and at INRIA on the subject of neural machine translation and more broadly on sequence-to-sequence prediction. Dr. Maha also graduated from Centrale Paris and École Normale Supérieure de Cachan. If you have any question during the presentation, please type them on the chat on Zoom or YouTube, and we'll make sure to bring them up at the end of the presentation. And please be sure to stick around for our networking session right after the presentation. We will break in smaller rooms so you get to meet and talk with some of the attendees. The presentation will last for approximately 30 minutes, followed by 10 minutes Q&As. Without further ado, Dr. Maha, please, the floor is yours.
So yeah, as I said, thank you, Iman, and thank you everyone for the invitation first and for the nice introduction. And I'm very excited to present my ongoing work at FAIR with the Moroccan community. It's always a pleasure. So the title of the talk is No Language Left Behind. It's actually the name of the team we have here at FAIR Excel, which is part of Facebook AI research. And the goal is to have like this large team. So like you can see on the slides, like 30 plus persons. And we're all coming from multidisciplinary areas. We have sociologists, we have linguists, we have data scientists, research engineers. And we all came together to work on this challenging task of machine translation, and particularly multilingual machine translation. So actually, the project was released today to the public, and we released all of our models, all of our data, and everything is open sourced. And I'll detail later all the aspects of the project that we are open sourcing. So I'll start with the motivation behind the project and some research questions that drove first the creation of this team within FAIRSeek, within Facebook, and what are the questions we're focusing on during this project. Then I'll detail the No Language Left Behind efforts or projects, focusing mainly on 2 points. As I said, there are multiple aspects to the project. Sociologists work on different aspects that I worked on. I'll focus on 2 aspects, which are data and models. I will share with you results of the NLLB model that we trained within this project. Okay. So the goal or the holy grail of machine translation is to develop a general purpose or universal machine translation model, a single model. It's not multiple models, but a single model capable of translating between any two languages in various domains. So let's say I have text in French, text in English, and I want to translate from French to English, and also from English to French, but also with the same model, I want to translate from English to Chinese, from Chinese to English, and many other languages. And the domains here means that we not only want to translate and say Wikipedia text, but we also want to translate chat text, health text, because every domain has its own particularity, but we want our model to be universal and adaptable to multiple domains. Okay, so there are more than 4,000 written languages, and if we extend that to non-written languages, the number goes up to 7,000 languages. And currently, Google Translate supports only around 130 languages, and Microsoft Translator up to 110 as of July of this year. So we ask ourselves the question: what does it take to break this barrier of 130 and increase that number to 200 languages, while ensuring that the quality of our translation is sufficient, and that we also keep in consideration ethical ramification of building this multilingual machine translation model. The second question raised in the field of machine translation: how can we improve machine translation in no-resource languages? Because most of the improvement we've seen in recent years focus on high-resource languages. The more data you have, the more you can train like more accurate models, good models. And if you have less data, you don't have access to good translation models. So like the rich gets richer and the poor stays poor. So our goal is how to train multilingual machine translation model that can pair data coming from different resource levels and maybe increase the transfer between languages. And so that's the amount of data that is high in some languages would help tasks in which we have very low amount of data. So as I said, multilingual machine translation is a multifaceted problem. And that's why this team is multidisciplinary. We have to consider or take into consideration ethical consequences of having a large multilingual machine translation model. We have also to include linguists in our efforts, but also a technical side of the project. How can we scale these large multilingual machine translation models? How can we incorporate large amounts available on the web, large amounts of data for training machine translation models? As you can tell, I'm from a technical background, so I'm only focusing on the last point of this big problem. So let's start with some preliminaries on multilingual machine translation. Here, NMT is for neural machine translation, but for now, I'm only the models I'm talking about is mostly neural. So let's say we have a source sentence in English, a source sentence in Wolof, spoken in Senegal, I believe, and then a target language, target sentence in RERY, which is Moroccan Arabic, and then the same target sentence in French. So our goal is to train a model or a probability distribution that will estimate the target sentence Y given the source sequence X, and the model will also be conditioned on the language of the source, which is LS. So in the first case, it will be English, second Wolof, and the language of the target sequence, so Moroccan Arabic or French. So how do we train or how do we learn this probability distribution or this model that will allow us to estimate the target sequence given the source sequence plus the additional metadata? Is that we have for a set of languages, here it's denoted with L, and we have training data in each translation direction. So a translation direction is sentences from a source language LS to a target language LT. And each data set I'll have a pair of aligned sentences. So in each pair, X is the source and Y is the corresponding translation to the source X. So we want to solve the following problem. This is similar to any deep learning learning model where you just optimize the maximum likelihood of the probability or observation of the the target sequence given the inputs, and plus some regularization term here, omega theta. But don't say, this is not very, interesting in itself. It's just like formulation of the problem that is very generic that will allow us to break down the problem into two components. So the first component is the data. So we need pairs from in multiple directions from LS to LT, and we need large amount of data to be able to train a very accurate or efficient model. So the primary source of data for training machine translation models is aligned bytext. However, these aligned bytext are very scarce. And as I said earlier, like high resource languages have a lot of available data. So if, you can guess, like the extreme right is the English. So we have high quality translation there because there are a lot of data you can train from, let's say, from English to French. Just the WMT data set, you have like 40 million pairs, and you can train large scale models and achieve near human quality translation in these tasks. On the other hand, when you move to the extreme left of the graph, we have low resource languages, and here we set the bar at 1 million. So this is the dotted line. So anything below any language with less than 1 million pairs is called the low resource, and anything above that is a high resource language. So you can see, like, for example, Findus Atlas Tamazight has only like 10K pairs, which is not sufficient to train a single bilingual MT model. So you need to do some tricks to be able to train a translation model on such low resource tasks. Moroccan Arabic is somewhere here, like 50K pairs. And then once you move up, you find a lot of Indo-European languages to the right, like English, French. I think Arabic is also a high resource language, like standard Arabic. So there's a lot of different languages in which you can find readily available data, but for I guess like maybe 70% of these data, we don't have enough data to train a bilingual machine translation model. When I say bilingual, just like training on a single task, the model will be only able to translate from a single pair LS to LT. So the first thing we did to extend existing data sets, so to train large-scale machine translation models, and what we call data mining, which is a tried and tested technique to increase the amount of data you have to train machine translation models in general, and particularly for multilingual machine translation models. And these techniques will leverage monolingual data, because what I was discussing here is bytext, which means that you have a text in a language LS, text in language LT, and you have an alignment. So you have data that tells you this is the language in language LS, and this is the corresponding sentence in language LT. On the other hand, we can also leverage monolingual data, which is just like a bunch of text in a given language. And then we want to go over these monolingual data and identify sentences that could be potentially translation of each other. So to do this mining, two major components to this mining pipeline. The first is language identification systems. You basically train an independent model to look at a given text, and will tell you with some probability this is French, this is Arabic, this is Chinese, and so on. The second thing we need for mining is multilingual sentence encoders. So once we have identified the language of a text, we need to train an embedding space that will map any given sentence in any given language into a common representational space, and then we can use some similarity search to find in that space sentences that are similar to each other, which means if they are similar to each other semantically, then they are probably translation of each other. So overall, we have training data for the language identification models as the LID. We do some iterations to improve the accuracy of the LID models. And then once we have this good enough LID model, then we can crawl over web data and run the LID system to identify for each span of text what is the dominant language of that text, run some filtering and cleaning, and then train sentence encoders to learn the multilingual representational space that will map all the sentences in any given language into a shared space. Then do some mining, basically similarity search in the shared space. And then once we have this mined data, we can also validate with the mined data if you can train a bilingual MT model. If we cannot train a bilingual MT model on this mined data, that means the mined data is not good enough, so we can just throw it away and maybe do some more filtering to limit the amount of noisy data that we can get from crawling the web. The second technique we used for increasing the amount of bytext or the amount of training data for these large-scale machine translation models is called backtranslation. I don't know if you're familiar with it, but it's basically you train a teacher model. So let's say you want to translate from English to French. You have a lot of French monolingual data. Then you will train the opposite direction MT model and then generate the source data, because generally MT models are more sensitive to the quality in the target size than the source side. So in this way, you'll have a clean target data coming from monolingual text or monolingual data, but synthetic or noisy source data. And once you have this half synthetic training data or half synthetic bytext for training MT models, you can add that on top of the mining data and the primary initial bytext data. So in total, we have in this NLB project, we have first NLB seed, which is our own clean bytext data, come mostly from Wikimedia and Wikipedia articles. It's very small scale. It's only up to 64 languages, and in each languages we have around 40K sentences, aligned sentences. So it's very limited in size, but it's very clean, and it's not dependent on any model. So it's high quality translation data. Then we have the public bytext. That's the initial distribution I showed of the amount of data we have in each translation direction. Usually public bytexts are noisy. They also come from crawling the web, running some mining, and so on, but they are already released and we just use them as is. The third source of data is the mine data. I explained the mining pipeline. And then we have a BT, which is back translation. And as I said, it's dependent on the teacher translation model that will generate the synthetic source data. So we experimented with two teacher models, MMT, which is a neural machine translation model, and SMT, which is a statistical machine translation model, and each have its own particularities. So we combine both to increase the amount of data that we can use to train our final NLB model. So this was the initial distribution we have. A lot of languages have less than 1 million pairs, but with the addition of back translation and mining, we can push most of the languages beyond the bar of 1 million translation pairs, which means that we can increase the performance or improve the performance or accuracy of machine translation models on most of the translation direction than most of the languages. The second aspect to the optimization problem, so we saw the data part, which is like going over all these data and trying to optimize the likelihood of the model distribution given this observed data. The second aspect is how we modelize this distribution of y given x plus the information on the languages. So we use, we didn't use any new architectures, basically transformer encoder decoder models, but we augmented these transformer models with the sparsely gated mixture of experts. The problem with these kind of models, let's start with the nice property of these kind of models, is that they allow you to increase the capacity of your model, but without increasing the flops or like the operations needed in each forward update of your model. So basically, at each forward update, you're only activating a sparse section or sparse portion of the model parameters. The problem with MOEs is that they overfit easily because you have this increased capacity. So you need to devise new techniques or new regularization techniques for these MOE models. I'll try to introduce a little bit of like what is an MOE models. So this is a transformer encoder block. We have layer normalization, multi-head attention, and feed-forward network. And this block is repeated n times, like n layers. So when you hear transformer base, it has 6 of these blocks stacked, and like some large models have 24 of these blocks stacked to increase the depth and the capacity of the model. So with MOE, we replace the FFN layer, the feed-forward network, basically 2 linear projections with a nonlinearity in between. And we replace the FFN with multiple FFN. So we have one FFN up to FFN-E. So usually E is up to 64 in our case. I mean, we have small models with 64 experts and larger models with 128 experts. So this is the term that will allow you to increase the capacity of the model. And then we have a gating network that will decide for each input token, what expert should I go through? Like let's have a first token that will go through FFN1, the second will go through FFN5, and so on. And so the total amount of layers is the same. This is n, but we don't replace all FFN layers with MOE layers, only a fraction of those. So each frequency f here, usually f equal to 4, and each 4th layer will replace the FFN with the FFN MOE expert FFN. So as I said, the FFN is a simple linear projection followed by a rectified linear unit, and then another linear projection. This is the expression of the regular feed-forward network layer in transformer models, except now that we have E of these, and we have a gating network, which is a softmax normalized linear layer that will project each token xt, that will give us a distribution across the E experts, and that will choose with top k gating, and we use k equal 2, so we'll pick 2 best experts, and then we'll have a weighted sum of experts as the output. So an additional loss term is added when you train MOE models. So as I showed earlier, we have the maximum likelihood of the target sequence given the input sequence. But we also add this regularization term, or maybe it's a load balancing term for MOE models that will allow us to distribute tokens equally or uniformly across experts. You don't want your model to always pick one expert and drop in the rest. So you try to balance the load of tokens across experts. So as I said, one of the major issues with MOE models is regularization, or like overfitting. So you can't easily regularize MOE models. So in this example, I have 2 languages, or 2 directions, 2 translation direction. We have English to Congo, which is a low resource language, and we have English to French, which is a high resource direction. So we start with a dense model. There's some slight overfitting on the low resource language, but then you add dropouts and issue solved. Then you train your MOE models, like the same architecture, except that you increase or change the FFN layers in the transformer model to add experts. So here we're hugely overfitting on the low resource language on top. We add some dropouts. We can still solve the problem, but not as much as we did with the dense model. So there is need for more regularization. We can't increase just the probability of the dropouts, because at some point we're going to drop all the parameters. So we came up with a new technique that we call EOM, which is expert output masking, which is a regularization technique that we can use on top of the regular dropouts. So I'm guessing everyone is familiar with dropouts. So you basically have activations, and you just zero out a portion of the activation in a neural network. So here, expert output masking is something different, something with that we came up with just for MOE architectures. And here we can see that with this additional regularization, we can further reduce the overfitting on the low resource language on top. So what is expert output masking? So as I said earlier, in a MOE layer, we have a gating network. So let's say here in this example, we have 3 tokens, each is a one color, and then we go through the gating network. It will tell us which experts are chosen. In this example, we only have 3 experts. So the first distribution will pick the first and the second. The blue one will choose the first and the third. The third token will choose the second and the third. So once we have this routing decision made, we dispatch the token to different experts. So here, this is the dispatching. So first experts, each expert will receive 2 tokens. And then once we have this, once each expert computes its output, then we mask the output of a random proportion or random portion of the expert outputs. And then we combine, as I said, because the final output is a weighted sum of expert outputs. So in this case, for the red token, we dropped 2 representations. So basically, there's no representation computed for the red token. For the blue one, we didn't drop anything, so no effect there. And for the green one, we dropped 1 representation, and we kept only one expert or 1 output. In contrast, overall dropout just, as I said, zero out some activations in the output vector. So here, like, we have 3 neurons in each representation, and we drop in some of these neurons. So one thing is interesting about the expert output masking is that it helps us strengthen the residual connection, because I don't know if you're familiar with the transformer model, but we have residual connections surrounding, in this case, the FFN sublayer, but the other sublayers as well. If you have this expert output masking drop in the 2 representation, then you're basically skipping a block, which allows the model to learn to rely heavily on the layer itself, but also the residual connection. And in the case where we have, in the case where we drop 1 expert and leave 1, it also allows the models to not rely heavily on some association of experts, because sometimes, let's say the green, they always pick expert 1 with expert 3. If you drop it at some random proportion or random portion of tokens, then you teach your model to not do this kind of association and to be robust to the choice of experts. So in the NLLB 200 model, we have this nice overview of the different contributions that we made. So I mentioned the NLLB seed, which is our clean small data set in 64 languages. We have public bytext, and we share scripts to how to download all this public bytext. We leverage monolingual data available in multiple of these languages. We train laser tree, which are the sentence encoders used for mining or learning the shared representational space where you mine for similar sentences. And then we have language identification and models and some filtering and cleaning scripts to run on these mined data or monolingual data. So this is the data side. In the modeling side, I talked about the mixture of experts, but we also experimented with the curriculum learning, self-supervised learning, which is another way to incorporate monolingual data into the training of your model, backtranslation, which is somewhat tied to the data, and then incorporating clean bytext, or maybe give like a special use for clean bytext in training back translation models. So all this culminate together to create the NLLB 200 model. We also, so we're not just training a model, but we're also releasing evaluation data in these 200 languages. I didn't mention that NLLB 200 is 200 plus languages. Actually 204, but only 202 with the bytext training data. So 200 is easier than 202 or 204. We also released toxicity lists. So I didn't talk here about toxicity filtering or how to reduce toxicity or hallucinated toxicity in NLP models. This is another aspect of the project that you can read on in the paper if you're interested. So now that we have all these data, we want to see if we really need to keep stacking on data, and do we really see an improvement in accuracy if we keep adding data, and how much or how much does these added data help the final performance of the model? So here we have, so in blue, we train the same model only on primary bytext data that include also our own NLLB, like clean bytext data, and additional noisy bytext. In gray, we train on primary plus mind data. And then the final one in green, we have primary plus mind plus back translation data. So in general, when we report accuracies or performance of MMT model, try to break down the directions we evaluate on into type of resource level. We have either high resource level, like languages in which we have more than 1 million primary bytext pairs. Low when we have less than 1 million, and very low, which is just a subset of low, we have less than 100K bytexts. And all, which is averaging overall direction regardless of resource. Then we split into type of tasks. We have English to X, which like translate from English to any other language. Then in B, we translate from any other language into English. And then XX and YY, we translate from non-English centric direction. So the source is different than English, and the target is also something else other than English. And generally, we see improvement across the board when you keep adding data, which makes sense. Like the deep learning, the more data you have, the larger the model, the best the accuracy. So here, the measure of accuracy is CHRF++. It's basically some sort of precision that look at character level, because the problem is that when you include or cover a large number of languages, you could no longer rely on like word level or some special tokenization. You have to come up with your own tokenization or go down to character level. But in any ways, it's a measure of accuracy, and it's a reliable measure to see how we are improving and how we are faring against state-of-the-art models. Next, we evaluate our models and compare to state-of-the-art models. Again, same metric here, it's CHRF and SP Blue. So SP Blue is another kind of accuracy metrics that relies on an SPM model, which is a sentence piece tokenizer model. So basically the difference is like CHRF is character level, SP Blue is a sub-word or a byte pair encoding level of splitting the sentence before computing sort of accuracy or position. In any ways, the higher the scores, the better. And we can see that compared to DeepNet and Delta LM, we're increasing the performance by a large margin. M2M100 is our previous work, I mean, not my work, but the previous work of the FAIR Lab team that was working on multilingual machine translation model. And DeepNet, I believe, is Microsoft, same for the LM. But generally, we can see an increase in performance across a set of languages. Generally, when you're evaluating multilingual machine translation models, it's rare to find that like released models that evaluated on all the same languages, because we're adding languages, but we can evaluate on where we overlap with these existing models. Another interesting result is that so when you have 200 languages in your data set or in your model, but you don't have, so when I said multilingual machine translation model, we want to translate from any one of the 200 language into any of the 200 languages. So in total, that's like 40K translation directions, but we don't train all 40K translation directions because we don't have data for all of these, but we're only covering, I think, approximately 250, 200 and 500. Yes, no. 2,500 directions. So most of them are English to many or many to English, and a small portion is non-English centric. So that's why we have what we call zero-shot translation. So you basically, your model saw the source language, saw the target language, but didn't see any pair in these directions. So we can still evaluate them because your encoder is familiar with the language, your decoder is familiar with the language. So you can just tell your model that this is my LS and this is my LT, and I want to translate in this new direction. And we can see that the performance is like decent in these zero-shot translation directions, which is very interesting. It's better than nothing. And a lot of these directions didn't have any existing evaluation data or models or training data or anything of the likes. So these evaluations are run on Flores 200, which is our own evaluation data set that we released. We previously released Flores 101 with 100 languages, and we extended these to Flores 200 to have a benchmark to evaluate these languages or models that expand to the 200 languages. We're only evaluating on the dev test, which is like a validation set, but the test set is kept like a secret behind some server for like benchmarking models. So other than our own Flores, we also evaluate on existing benchmarks for MT. If you're familiar with MT, then you know of WMT, of IWSLT. These are mostly in the news domain, but like Flores is the Wikipedia domain, and we want to see if our model can do well in other domains other than Wikipedia. Mafan is recently published evaluation data also from, scrolled from the web, so it's multiple domains, but it's focused on African languages. And we also have TICO, which is a COVID initiative. So most of the text is in the health domain. And across the board, we outperform like existing state-of-the-art with some like bad performances in some specific directions, but overall, we improve on state-of-the-art from previous state-of-the-art. And if you're very interested in these, you can find like the detailed results in the paper. Another thing we wanted to test is whether this NLB 200 model trained on public bytext, so coming from different domains, but with a focus on Wikipedia, can translate in other domains, or can we fine-tune this model to a specific domain and still see gains in performance? So we have our own NLB MT test sets. We have training and development and test data in this released new data set. And we want to fine-tune NLB 200 on this specific domains and see if we can still increase the performance. This is a common practice in NLP, and I guess in machine learning in general. You want to release a model, but you want to allow the community to fine-tune the model for their own specific needs. And in general, we can see that we can increase the performance by fine-tuning. We're not like doing very bad on any specific domain to begin with, like without even fine-tuning, but we can still gain a few CRF points by fine-tuning on the specific domain data. So to finish up, we just released today this or just open source today, all of our models. So we can find the project webpage. So just Google No Language Left Behind, and you'll find the Facebook project webpage, a link to the paper, and so it could also be published in archive soon, I believe tomorrow. We have a blog post about the model, how to train it, how to fine tune it, how you can use our models for your own purposes. And we open sourced the model, like the MOE models, but also the dense models, and how to run the mining pipeline, how to do back translation, how to basically do everything we did in the paper step by step, and how to fine tune on your own data. There'll also be a Hugging Face integration coming soon. I know if you're familiar with NLP, then you probably know of Hugging Face and the huge effort they do in open sourcing transformer-based models. And we're also releasing Flores data for evaluation, as well as NLLB seed I mentioned earlier, and NLLB multi-domain data. So thank you for your attention. I'll happily answer any of your questions.
Thank you very much, Dr. Maha, for this very informative presentation and talk about the No Language Left Behind project done in Meta. So we can start, we have a few questions and we can start our Q&A session. So I will start with the first question from a participant. He is asking about the Moroccan context about Darija. How can we help producing training data for the low resource Moroccan language like Darija and also Amazigh?
How can we gather data, or what is the question exactly?
Yes, how can we produce training data?
Oh, well, so training data, so either it's public bytext. So let's say, so like the most commonly used data is like the Bible. We have the Bible in multiple languages. You just take that and you train your model with it. So I guess would be the same thing if you have like Quran translated into other languages, and you have aligned data, or like some government documents. Like I've seen multiple data, like for example, India, they have 10 official languages, and whenever they release some manuscripts or some document, they provide translation in these all the languages of the country. So you can find like aligned data from there. That's like readily available public bytext. So someone aligned this data, someone like a human translator went through the data and created bytext. The other way is like what I talked about, is like mining. You have just monolingual data. Let's say we go over Wikipedia in Arabic, in Moroccan Arabic. We just use these sentences. This is monolingual data. And we can also go through Wikipedia in some other language. And then we embed them in this shared space. And we can just hope to find some parallel data there, but it will be noisy, not the same quality level as like human aligned bytexts.
Thank you for this clarification. So which brings us to another question about the data set used in No Language Left Behind. So how massive was the effort to collect the data, and what actors did you involve in the annotation task?
Yeah, so I didn't work on this. So when we were like writing the paper, I was like amazed at how like the amount of effort when I was just reading through the data gathering section. It was very amazing. Like for some languages, like took a year to just gather 1,000 sentences, because you have to go through a lot of quality assessments of human translated data. You have to pick a translator with some level of qualifications, and once you move to like low resource languages, you can no more like be very picky in the like quality, in the quality of translation. So you just have to make some trade-offs between quality and amount of data you have. But I think like some language took approximately a year to just gather Flores 200, which is like approximately 1,000 sentences in each language. This is not much, but still it takes a lot of data. But that's for like evaluation data. I want our evaluation data to be proper and humanly aligned, not so much training data where you can afford to have some noise there. So yeah, but also like for the mining, I think they gathered like, I think it's like 40 petabytes of data for mining. So we have like a lot of monolingual data. You just crawl the web, you gather a lot of data, but you need a lot of compute power to just embed all these sentences and then do some similarity search. So it takes a lot of time to like on the monolingual data side, like even like automatic stuff without like human experts behind. And then for like human aligned translation, that's another story. But it's all like detailed in the paper, and there's a lot of, I mean, they also made like, they also conducted interviews with like low resource language speakers to understand like the need or what do they need in a multilingual machine translation model, what are the use case they can think of for these models. So there are a lot of aspects to the projects that I mentioned earlier, like mostly about like ethics and sociologic aspects of such big models.
That's impressive, especially that it took long year to work on for this project.
I joined 6 months ago, but the project started like a year and a half ago. So it takes a lot of time.
Yes, that's for sure. I mean, it's a big project. I mean, it's an inclusive project for all languages. So we can go to the next question. It's from Ahmed. He is asking about the language identification. How did you encompass and add low resource languages, as the IFT LID only supports some specific languages?
Yeah, we use for like LID, we use fast text. It's also like a Facebook model, and we trained it on additional monolingual data. We just not just take an existing LID system. We have like, we did our crawling of the web. We have some labeled data, but we do LID and we reiterate to keep like adding languages. So that's like LID part. I don't think there's much for LID, but like for like laser, which is like sentence embedding, it's like you do a lot of like mining within language families. So let's say you have a sentence embedding model for like modern standard Arabic, MSA, but you want to expand to like other Arabic dialects. So it's better to just expand some existing model or like have a teacher model that will teach smaller models like within the same language family than train like some language model from scratch.
Thank you for the answer. So in the same context on LID models, how is human evaluation involved in the language identification training loop?
Yeah, I mean, we have like human evaluation for like MT models, but for LID, so for human evaluation, so because like LID is just a simple linear classifier, sometimes we have like linguists look at why like these two languages are mistaken. I think we have like some special languages that are very difficult to identify. Like you have, I don't know, let's say, we don't have it in the paper, but let's say you have like Moroccan Arabic and Algerian Arabic. Sometimes you can have a sentence that is the same in both languages, but your LID model will be mistaken because you told the model while training that this is Moroccan Arabic and not Algerian Arabic, but it could be as well like Algerian Arabic. So in some cases, we just want to not penalize the model for identifying like languages that are very similar. And we just look at what is the how can we interpret the model decision, and we can then incorporate like similarity between languages into the LID pipeline. That's where like human evaluation and linguists analysis came into play.
Okay, that's good to know. So we have also another question from Nerman. He is asking that abundance of English compared to other languages, like you said at the beginning of the presentation, we have a mismatch between high resource languages and low resource languages. So which means that we have difficulty in training. What about the techniques that you use to overcome the long tail distribution problem?
Yeah, I mean, for the long tail is just that's why we have like multilingual models. Like if you rely on just bilingual models, then we're not going to match the quality of translation in high resource languages. Like if you take, I don't know, like Wolof to English, you have like very few sentences, and then you train exclusively on those, then you're not going to improve the quality of translation. But what we leverage with multilingual machine translation is the transfer between languages. Like if, as I said, if you have like languages within the same family, like linguistic family, then they can boost each other up. So if you have just 100K in each, then in total you can reach 10 million in a given language family, and that will improve the quality of translation. We're not going to match the quality of English, because even like with mining and back translation, you end up with very large amount of data in English, and that's why like a lot of multilingual machine translation models, they usually just focus on into English and out of English, because you have a lot of data map into English, and very few models evaluate like non-English centric directions. I don't know, let's say French to Moroccan Arabic, and French even is high resource. Like let's just say Moroccan Arabic to Levantine or something like that. So it's very difficult to train these unless you just leverage the transfer between languages. Your model can see different languages, but also can learn similarity between languages, and these similarities help beyond like increasing the amount of data.
Thank you so much, Dr. Maha, for your answer. And we have another question. I know that there is more detail in the paper, but we will take the opportunity of having you today with us and ask you about the EOM regularization that you developed. Was it specifically developed for this work, or it was a general technique?
No, it was developed. I mean, MOE, like mixture of experts, existed before. We just like added this regularization technique. It's not very complicated, just like a very small extension of Dropout. But yes, it was developed for this project.
Thank you, Dr. Maha. So we have another question from Abdulrahman. He is asking, does the final model exhibit or show any few-shot learning capabilities?
Well, so I chose 0 shots, so I guess 0 shot is better than few shots. But I mean, you can call like what we did with the with fine tuning sort of few shots. We only trained on. I mean, it's not few shots. It's like a 1,000 pairs we trained on. Then we evaluated within the same domain. We didn't try like just training on maybe 5 sentences and see. But 0 shot is, I guess, more difficult than few shots. And we did a lot of evaluations. So I guess we trained on 2,400 directions, and the rest of the 40K is 0 shot. We didn't see any training data on these directions, and we can still evaluate the model.
Thank you. So I will end our Q&A session with this question from Ahmed. He is asking about the data sets used in the No Language Left Behind. Are they open sourced?
Yes. So what we did, so what we call primary bytext, which is like data we found on the internet. So NLBC is we created it ourselves, and we are open sourcing it. Public bytext, let's say WMT data or IWSLT data, like existing data for training machine translation models. Just go over what's readily available, and we download it and train on it. And we have also like releasing scripts on how to just download this data. Some would require like some signing on into some platform to download it, but like not our own, just like because of rights to these data sets. Mine data we're releasing the how to create it, not the mine data itself, and the same for back translation data. So everything we use for the model is open sourced.
Thank you, Dr. Maha. So we have so many other questions, but I will invite our participants to join us in the breakout session and ask our speaker directly. So we have two breakout sessions. It's the first one is the speaker ask me anything, and the second one is to network between our AI community. So we will have 20 minutes and then we will go back to the main session. But first, I will just stop the